All right, you guys, we have an exam next Friday, week from today, in class, 50 minutes. The questions will be similar to those that you read in the self-test exercises and the readings. My plan is to do an in-class review of the material that we've done on Wednesday, so next Wednesday. And at that time, I'll also give you a sample of what kinds of questions, not a full-blown test, but just 4 or 5 different kinds of questions that you might encounter on the exam. Any questions about that? If you have a conflict, some sort of excused activity, by all means, come talk to me after class and we'll make arrangements. My plan today is to finally sketch out the bisection function a little bit and talk a little bit about how one might offer default value. In other words, if you look at the, I'll show you that in a minute, how you would offer a default value. And then Tong will do her presentation. I have your PowerPoint here, so if you just want to, you don't have to do anything, yeah, unless you need like something else. But okay. And if I have time, I will continue a discussion about why do we care about functions? Why do we need functions? Why are functions important in C++? So without further ado, I want to remind you of the function that we wrote last time, the letter test function. And really just the anatomy of building your own function. There is the declaration at the top, and this is really just syntactical. It's really just a way of telling the compiler that if you encounter this name isLetter while you're compiling the main program, do me a favor and check to see whether it has the right number and type of arguments and whether it's in a proper context. Like, is it in a place where a bool would make sense? That's all it does. And then the compiler goes through and says, isLetter, do I know about that? And it goes up here and says, oh yeah, and a character is okay, and a boolean. Okay, so I'm okay with that. And it gives it a pass. And then it goes on, at a later step in the compilation, it actually turns these functions into machine code. It turns them into instructions that the CPU on your machine can actually understand. We talked about that way back on day 1, about how a compiler is really just a translator from from C++ to machine code. And what happens is it compiles this main function, but there's kind of there's a hole in it right here where it doesn't know how to do this. And then it compiles this thing, and it just so happens that this guy will fill that hole precisely in the right way. And then the last step, so the compiler compiles this into machine code and this into machine code. And then the last step is to link these two guys together like perfect jigsaw puzzle pieces. And that gives you a fully functioning executable. You'll see hints of this, and I'll talk more about why this is an important idea as we go on in the semester. At some point in the semester, probably maybe homework 5, maybe homework 6, we will start taking our programs and splitting them up into different files. The same program will occupy 1, 2, 3 different files. And it's for this reason that C++ behaves the way it does, where you declare a function here and then you define what it does somewhere else. All right, so with that in mind, Rachel.
The isLetter, I'm kind of confused about what that is. Is it just a variable? Can it be replaced?
The word?
Yeah.
I could call it any legitimate variable name. So I called it isLetter because it's sort of descriptive of what the function actually does. It tests whether this thing that you're passing in is a letter. In a sense, it asks the question, is letter? In a very sort of choppy English way. Is letter? Yes. Or is letter? No. And that's why I named it that. But I could call it anything. Does that answer your question?
Yeah, and
Ish?
then under your if statement where you have is letter M.
Mm-hmm. Okay, so let's talk a little bit more about this. You declare the function up above. You define what the function does down below. Declaring it and defining it, though, you can do that as much as you want, but you'll never actually use it unless you invoke it, and that's what happens here in main. Here's where it actually is invoked, where it actually does its job. And I can use it more than once. I could have other characters. For example, I could see if M is a character, and I could check and see. I could do, let me think about this, n equals m plus 1. Let's do that. And then I'm going to copy this whole block, and I'm going to replace this with n, and n, and n. Okay, let's run this thing. And I'm going to plug in A. What do you think is going to happen?
It'll tell you A is a character.
It'll tell me A is a character. Is that it?
It'll tell you B.
It's going to tell me B is a character, because when I do n equals m plus 1, what does that put into n? Puts a B in there, right? A plus 1 is B. So it's going to tell me A is a letter, B is a letter. Okay. What would be another interesting choice? Z, right? Z is a letter, and left curly brace is not a letter. This brings up one of the really important points of functions. I can write the function and what it does once, and I can use it as many times as I want on different letters in different contexts. So this is sort of like I just wrote my own sign function. I can use sign anywhere I want on any numbers I want. I can use this function anywhere I want on any character that I want.
So when you say is letter and then M in parentheses, where in the past you just said like if n is greater than or equal to 0, is that saying that if n is letter, if that's true from the bottom part, the defining, then you run that in?
Right, so how does if work? If will do the top part if the thing in parentheses is true, and it'll do the bottom part if the thing in parentheses is false, right? So in order for this program to run, it has to figure out the thing in the parentheses. Is it true or is it false? So it gets to these parentheses right here, and it doesn't know what to do. So what it does is it evaluates this thing in here. How do I evaluate it? I take this n, I plug it in down here for C. It's going to turn into true or false. That's the return value. So this true sort of comes back in this Boolean slot. It'll be either true or false. And then if it's true, it does the top part. And if it's false, it does the bottom part. All right, let's talk about another function. Again, not a really complicated function, but I want to show you that there's a little more flexibility to this than you might expect. Let's do... All right. So we'll write a function to compute the average of two values. All right. So how many arguments does this function take? How many things do I feed into the function? 2. What's it going to do inside? What's the formula that's going to happen inside? Add them together, divide by 2. What am I going to do with that number? I'm going to return it back to the calling function. Okay. What would be a good name for this function?
Average.
Average or mean. Either one. So let's declare it. So to declare it, I need to say what's the return type, what's the name, what's the number and type of arguments. So what is the return type here?
Double.
Double. Why not int? I'll lose some precision at best, right? So I want the average of 4 and 5 to be 4.5, not 4, or actually 4 is what it would be in integer arithmetic. So double. We decided that a good name would be average. Always want to name your functions in a meaningful way. It takes 2 arguments of what type? Both doubles. Again, this is simply declaring the function for the compiler to say that if you encounter this word average, this is a function. It should have 2 arguments of type double, and it should be in a place where a double makes sense, because after it runs, it's going to turn into a double. Yeah?
Is there a way to make a function that has an undecided number of terms and you're dividing by an undecided number of terms? Like,
actually, no, not what you're thinking. So suppose I want to write a function that averages 3 numbers, a function that averages 4 numbers, a function that averages 5 numbers, an arbitrary number of numbers.
Yeah.
I have to take a different approach,
Okay.
and we'll talk about that.
Yeah.
So down below, traditionally, is where we define the function. And it's at this stage I have to introduce what? Do you remember? The dummy variables, the placeholders for how the function is defined. Now, I'm going to do this slightly inefficiently to make a point. So I'm going to declare a variable inside my function, call it m for mean, and I'm just going to assign the value x plus y over 2 to it. So what's sitting in m after this declaration of m? The average, the mean. What do I want to do with it? I want to give it back to the calling program. Let me go up here and just see out average 1, 2. Let's do something slightly nicer than that, say 1 and 3. And I could use it again and again. So let me do. Let me put 2 in here now. 1.5. So I can use this function as many times as I want with as many different arguments as I like. Look at what happens if I try to do, say, 3 things. That's kind of weird. It says there are too many arguments for the function double, average, double, double. And it tells you where the error occurred, line 13, and it tells you where the function was actually declared, in case you're interested in that as well. It similarly will work with too few arguments. Oops. And it's even smart enough to tell you that there were too many or too few. It's rare when the debugging when the error messages are actually helpful, but in this case they are. So this is a really common error, misusing a function somehow. I want to try one other thing. I want to try a float. And let's use A equals 1 and B equals 3. And let's try the variables A and B in there. Now, what's weird about this?
You're putting a float, not putting a double.
I'm putting floats into a place where doubles are expected. What do you think will happen?
Whatever your A and B were, at some point will they use them? Oh yeah, there's some arbitrary values.
It'll either force them to be the double numbers, or it'll just not work.
Let's just see. So compiled without any warning at all. And it appears to work. So this is an automatic type conversion, and it's such a safe type conversion that you don't even get a warning, right? You can never lose information by converting a float to a double. Does anybody know the difference between a float and a double? It was in the readings, but I didn't talk about it. It's okay if you don't remember. Remember when we did machine epsilon a while back? We did 1 plus e greater than 1, I think it was. And after a while it crapped out and e was around like 10 to the minus 16. If I had done that same exercise with a float instead of a double, e would have been 10 to the minus 8. So floats are less precise. They carry fewer significant digits than doubles. So why on earth would I ever use a float?
To save resources.
To save memory. If I have a program that declares billions and billions and billions of doubles, and I change them to floats, I suddenly am using half the memory, because a float is half the size in memory as a double. Sorry?
As long as you don't lose anything, that's a good idea.
Yeah, if you need the precision, then that's not an option. But if you don't need the precision, use floats. Let's try... Okay, so now I've got a couple characters, and just kind of coincidentally, I'm sticking the character A in the variable A and the character B in the variable B. Let's see what happens. Seems okay with that. And looks like it's okay with that too. Automatic type conversion. Does the 97.5 make sense? A is 97, B is 98. It's all good. Okay, so there's some forgiveness there, I suppose. I think if we switch this around, I'm trying to make an error here. I think if we switch this to float float, and then we try to stick a double in, it'll yell, or at least warn us. I would hope it would warn us. Yes, thank you. Well, it didn't. There might be a flag to the compiler to tell it to be a little stricter about that, and maybe I don't have that flag on. That's something that I would worry about, because I would worry about sending this guy in and losing precision. Anyway, okay. So you can have functions with 2 arguments, and all you have to do is list the type of each argument separated by commas. There's one other issue that I want to talk about here that's not really important to this particular example, and that is order. So in this case, order doesn't matter because the average of A and B is the same as the average of B and A. But if you have another function where order does matter, make sure that your placeholders, that you respect that order with your placeholders. Okay? So this X is always going to whatever's in this slot is always going to end up in the X slot, and whatever's in the second slot is always going to end up in the Y slot. And if you swap them, you may not get what you want. Like I said, in this case, it doesn't matter because this is what we call a symmetric function. The order is interchangeable. Questions? All right, let Tong do her thing, and then I will come back and talk about the bisection method. I forget how to do full screen. Does anybody remember? Emily?
Slideshow?
Slideshow? I don't use Windows.
Or
No,
yeah,
I
you
can.
can.
Yeah.
Oh, I'll let you do it. I don't use Windows enough to know.
Oh
What?
no. Oh. Okay. Okay. What I'm going to talk about is what is artificial intelligence and does it exist? The Wikipedia definition of AI is the intelligence of machines and robots and the branch of computer science that aims to create it. And the AI textbook defines it as the study and design of intelligence agents, where an intelligent agent is a system that perceives its environment and takes actions that maximize its chances of success. So my personal image of AI when I first heard the term, and based on these two definitions, something like that, or a little less scary and cuter, at least something like that. But there are many different definitions of artificial intelligence, and according to John McCarthy, who is the guy that coined the term in 1955, according to him, that AI is the science and engineering of making intelligent machines. So AI definitely exists very commonly in our daily life, especially in technology industry, such as manufacturing, medical diagnosis, data mining, logistics, and like something that you play in your computer, like the chess games and the Tetris thing, that is also AI. It may not be called AI anymore because there's no further improvement on them or further development of them. So they were AI when they first came out. There are definitely different types of AI, which has the AI that we are talking about now is called weak AI, and it's defined as the artificial intelligence that used to help people to solve problems or perform tasks that is very hard for human beings to do. But there are also different AIs, and it's called strong AI, which was the picture like scary thing that I showed earlier, and it's defined as the artificial intelligence that matches or exceeds human intelligence, which is the intelligence of a machine that can successfully perform any intellectual task that a human being can. This is more interesting and exciting because we are literally wanting a machine to have feelings and emotions. And so currently what the strong AI researchers are doing is they are trying to put biological brains on functioning circuits or robotics and hoping they can develop some self-awareness or emotions or feelings that human beings have. Currently, I don't think there's any real AI product or strong AI product that's like real that we can see them, because for a human being to have feelings or emotions, we have to have chemical memory that to store all the experience that we had in order to perceive what's coming now, or like in order for us to do tasks that we just normally do. But it's very hard for a machine to develop those kind of senses. So, I mean, biologists and neural or computer scientists are really trying hard to combine like human brain or neurons and all the stuff that in our brain, our body, onto the machines. But as we can see, it's a very hard task to accomplish. The next thing, Well, the last thing that I want to talk about is AI and C++. We can actually create AI ourselves, and what we're doing actually can be categorized into one type of AI. We learned about Boolean expressions and with true statement and false statement. So actually what we're doing for this week's homework can be categorized into one type of AI. We can find like the solutions of a function, or when the function equals to 0 and what so not. So AI, like in general, AI definitely exists in our daily life, and it could be the computer that you are using, your calculators. There are just many different branches of AI and definitely exist in our lives. Are there any questions?
Also with me.
Go
ahead, Lauren.
Do you know how far they've gotten in producing some sort of, or how close we've gotten to strong AI?
I think they used red brain, and they were trying to put red brain on like a machine, and the hope is the machine can stimulate everything that's identical to what a rat will feel. I think they've successfully put the brain onto the machine, but it's very hard to get the result. It's hard to know that whether the machine knows that what the machine is feeling or it has emotions, because there's no way for the machine to tell you. So I think it's not hard to put the brain on something, but it's hard to make them work together and finally develop this product. Was there a question?
Yeah, so you know the IBM computer Watson?
Oh yeah, I read about it.
So I don't know if you know a ton about this, but I was always curious in how it was able to respond to the questions it had never before encountered. Like, what sort of code would you have to give a machine to be able to interpret something it hears that isn't necessarily in its database already, and then respond to it?
Well, I heard of Watson, but I never looked into that. But I looked into Siri.
Okay.
I don't know if they're similar, but according to Siri, I thought Siri was type of strong AI, or can lead to a strong AI because it's very smart. And the thing is, we're saying how because Siri needs to connect to like iCloud or something that has internet access, so the engineers or the scientists in Apple can constantly putting new terms or new codes into Siri so that it keeps with the development of our language or our culture. So like a fixed computer that you cannot really put any new codes or new things in, but with Siri, what they do is they constantly changing the codes in Siri, so make Siri really like updated. So I guess that's one way of doing that. Yeah.
Yeah, I might have missed this, but what's the criterion for strong AI versus weak AI? Is there like one specific thing that moves from weak to strong?
I would say strong AI associates more with human beings' senses. So like consciousness or self-awareness and like intelligence. So anything that has those kind of characteristics might fit into the definition of strong AI.
It'll be hard to measure.
Yeah, definitely.
Okay, I think that's all we have time for. Thank you. One of AI's biggest problems is definition of what it actually is. It's sort of like I'll know it when I see it. I have a feeling, though, what's going to happen is it's not going to be some big announcement someday that there's this strong AI in this lab somewhere, but it's just going to sort of surprise us one day. There's going to be some weak AI that just... I think we're already kind of seeing it. Like, you know, one could argue that that we are now... Our intelligences are somehow different now than they were 20 years ago, because we have instant access to almost all information. And so we're just so much more capable now individually than we were 20 years ago, because we have all of this information at our fingertips. We're just amazingly more, I don't know what the right word is, intelligent. And so I feel like that's kind of the way it's going to go, is there's just going to be this kind of growing symbiosis between what we do and what our machines provide us, and that will change our intelligence, as it already has. But there may be strong AI at some point, too. All right. So let's talk a little bit about the bisection function and the heart of the bisection function. I took great pains to try to lay out the algorithm for the bisection method in this outline. And I did that for a reason. This outline nearly mimics what your code will look like in your bisection function. So let me remind you that down at the bottom, I'm asking you to use this function declaration verbatim, literally copy it out of the web page and paste it into your document. And it's inside the definition of this function. So where does this go? This goes at the top, right before main. And where do the guts of that thing go? Down at the bottom. So what will be in the guts of this thing is essentially this outline. If you look closely at this outline, you'll see that it relies on 3 external values. Madeline, did you have a comment?
I have a question about looking at the bottom. I thought that you declare the variables, the dummy variables at the bottom.
It's totally, it's whether you put the dummy variables in the top at the declaration is optional. And lots of programmers will put dummy variables at the top to make the declaration at the top more descriptive to somebody that wants to use it. Okay? So they're not necessary, but it's a way of giving the user of your function a little more information. Danielle, comment?
Yeah. So the function that we're doing the bisection on is just that function. Like for all cases, we're just doing that.
Yeah, you can change that function to anything you want. But yes, the program, just if you're messing around with it, why don't you, before you submit it, why don't you make it that? Because then it'll be easier for me to at least start testing it. But I will, one of the things, part of what I'll do when I'm testing your program is I'll actually change that function to something else, just to make sure that you've written your program in generality with respect to F. So let's talk about what external data. So A and B are kind of preliminary steps. Enter the desired accuracy, enter 2 values where the function has different signs. Find the middle of that interval, choose the left or right side based on this if statement, and then do it until this thing becomes less than the tolerance. It's not an accident that the bisection function at the bottom only has 3 arguments, because this algorithm only requires 3 external values in order to be well defined and run. And those external values are x left, x right, and the tolerance, E. So you feed those 3 values into this function, and now it's ready to go. Well, you might say, wait a minute, there's x mid there. Doesn't it need x mid? And what's the answer? Does it need x mid from an external source? No, x mid is actually calculated from the given data, x left and x right. So x mid is what we'll call a local variable in the function. And I just showed you an example of a local variable here. What's the local variable in the average function? M. It didn't come in from the list of arguments. It was declared inside the function, and then it was used as part of some intermediate calculation. All right, let's talk a little bit about how this is going to work. What kind of loop? a while loop. What's the condition on the while loop? I'm going to start writing here. So we'll have a while loop, and the condition, what is the condition going to be?
Well, we have a couple if statements, right? Like talking about the right and left side.
We still gotta get.
While it's not equal to 0.
So we want.
While the tolerance.
Oh yeah, yeah.
If while the tolerance is too big.
While the tolerance is too big. So it's this guy here, right? While, so it's, but this isn't it. It's while what?
Oh, well, what you put in.
While this is bigger than that, right? We're going to run this loop while it's bigger than or equal to.
Okay.
XL is the left endpoint, XR is the right endpoint. ABS, what's that? Absolute value. Why is that important?
Because it's the magnitude of computing.
Yeah, all I care about is the magnitude. In this case, it's not really going to matter. I could just use XR minus XL, and that would always be positive because the right endpoint is always going to be bigger than the left endpoint. But I just want to use this notation because this is such a common thing to do in in numerical analysis. To run an algorithm until some tolerance is met. And it's very often the case that the tolerances, even though the points are getting close together, they might be flipping back and forth. And so you just use the absolute value. And so it's just a habit that I have of using absolute values whenever I'm testing a tolerance. I want these 2 points to be close together. And absolute value measures distance between points. TOL. So I'm just using the argument down here.
Okay.
All right? All right. Now, we're going to do, the while loop is going to run until the absolute value of x left minus xr is less than tolerance. Go ahead.
How do we actually declare the tolerance? I don't know if we...
Yeah, I'm going to talk about that in 5 minutes.
Okay.
But for now, just assume that it's been declared, that it's been given to some value, 10 to the minus 4, say. All right, you're inside the while loop. What happens inside this while loop? Well, let's stare at the outline. What do each of these if statements depend on?
What you input.
They depend on the existence of x mid. So what's the first thing I have to do in the while loop? I have to compute x mid. Oops. Now what? If statements. Okay. If f of xl is times f of xm is less than 0, then xr equals xm. I would just use xm, not x mid. Else, if bigger than 0, then xl equals xm. Else, f of xl equals, f of xl times f of xm equals 0, then stop. Why stop? And which one is the solution? Actually, xm. So what's going on in so let me just sketch out something like So if f of xl times f of xm is less than 0, say, I might be messing that up, hold on, less than 0, good. In that case, let's go look at a number line, and we have xl here and xr here, and we have xm here, and we have the function passing through here. F of xl is this value down here. F of xm is this value up here. When I multiply those two guys together, positive or negative? It's negative because they have different signs. One's above the x-axis, one's below the x-axis. What that means is the crossing has to be on that side. And so what we do is we take the right endpoint and we move it to the middle and we start over again. So in this case, xr equals xm. Else, you know, we could also do this. Else xl equals xm. And then we could have like a separate case if xm equals, sorry, if f of xm, then just break or return. That might be a little cleaner.
On your drawing, what does the thing at the right say?
The far right is an xr, and this is an xl. Sorry about that. The edge of the screen on this leaves a bit to be desired. So does my handwriting, but. Okay, so we've got the while loop condition. Then inside the while loop, we compute x mid. We test to see if f of xl times f of xm is less than 0. If that's the case, then we move the right endpoint to the middle. Otherwise, we move the left endpoint to the middle. And if it happens to be the case that the midpoint is f of the midpoint is 0, then we're just going to quit this loop altogether. But if that's not the case, where do we go next? What happens now? Ideas? Well, I want to know, like, after I do this one sweep of the while loop, what happens? I go back up to the top, right? And do I have a reasonable expectation that eventually this while loop will stop? Actually, I do.
Well, like, but even then, your x is out.
What's happening to the distance between xl and xr every time you go through? It's halving, exactly right. So I can tell you, if you give me tolerance, I can tell you pretty much exactly when this thing is going to stop. Right? It's just essentially powers of 2 dividing by 2 until, so yeah, I have every expectation that this loop will stop. Of course, Danielle was correct. If my tolerance is sort of too small, you know, back to the machine epsilon kind of thing, I could mess things up in that way. But we're not even close to that issue here. Yeah, these XL and XR are inexorably getting closer together. Because what happens every time through is we cut the interval in half, and then either the left endpoint goes to the middle or the right endpoint goes to the middle. And so XL and XR are necessarily and inexorably getting closer together. So this will stop. Okay, let's talk about default values really quickly here. go. Okay, so let's pretend that we have a default tolerance. 10 to the minus 4. And we do something like cout enter tolerance. And there's a tradition in Unix to put default values in square brackets. So I'm going to open a square bracket and I'm going to print out what the current default value is. And then I'm going to close my square bracket and then finish the prompt. Grr. Let's see what that looks like. So enter tolerance, and I can hit enter and it's just going to sit there and it will insist that I put in some value. So this is not quite what we want yet. So I can do that, and when I do that, what happens is it comes down, it prints out enter tolerance, and it shows the current value of tolerance. When I type in a value, that previous value gets overwritten, right, by whatever value I just plugged in. What I would like to do is devise some way of keeping the default value if I choose to just hit enter. And let me show you the magic there. I need a curly brace there. Okay, here's what you'll need to accomplish the default tolerance. What I did, the only thing I really did was I surrounded the cin tolerance with this if statement. And it uses a feature of the cin function that you're not aware of yet. Let me show you how this works. So the tolerance, the default tolerance is there. I'll just hit enter. And now that appears to be working. Or I'll type in 0.002. So it's now successfully distinguished between me entering a number and me just hitting enter. How does this work? Peek. What it does is you type out the prompt, and then the if statement comes along and it tries to evaluate this. And the way that it evaluates this is it says, oh, I have to go get some input from the user. So the program halts, and cin, this cin right here, is halting the program and it's waiting for you to do something. You have two choices. You punch in a number and you hit enter, or you hit enter. If you punch in a number and hit enter, Peek is going to look out there and it's going to see the next character that's coming in is not an enter key. Therefore, that means there's a number there, and I'm going to read it in. On the other hand, if I just hit enter, then what's the next character that's coming in? The enter character. And in C++, the enter character is \n. If it sees a \n out there, this is what? False. It skips this, and it just keeps the old value of tolerance. Really simple. What's new here is the peek thing. Peek gives you a way of looking out there and seeing what's coming in without messing around with it. It lets you see what's the next character coming in, but don't read it in. Just go peek at it and then leave it there. it's a non-destructive way, in a sense, of looking at what's going to come in and lets you make a decision on whether you should read or not read. So use this recipe to do the default tolerance that I asked you for in the assignment. Request the desired tolerance and offer a default tolerance of 10 to the minus 4. Let me remind you, or let me just leave you for the weekend with a rerun of my bisection method. So this is precisely what I just showed you. So it's the bisection method for x squared minus 2. Enter the desired tolerance. So what's holding this program up right now? What in the code is holding it up? The peak. The peak. It has nothing to peek at yet. So it's just waiting for you to give it something to peek at. So if I hit enter, then it's satisfied and it leaves the tolerance the way it should be. And then I'll do an initial interval. And there's my output. On the other hand, I can put in 10 to the minus 3, for example, and 1 and 2, and get slightly less accurate result. I'm sorry, I know I'm holding you over time here. The one last thing that I want to talk about is this thing here. Test this condition. Before you start your while loop, test this condition. Why? Yeah, if not, there may not be a crossing, right? If the left endpoint of the function is above the x-axis and the right endpoint of the function is above the x-axis, there may be a crossing in there, but there may not be. And I'm asking you to just abort at that moment. Similarly, if it's below, if they're both below, there may not be a crossing. So have fun with that, and I'll see you guys Monday.
So do you want my, oh yeah, record error.